So we have one lemma to prove, and with this lemma we almost finished the Kalinin-Katok theorem. So let me remind you once again what we were doing. So we had this parametrizations of this coarse direction, which are diffeomorphism in such a way that if we define alpha xi of t as definition is doing alpha of t in these charts. So this guy, which goes from is linear, and as I said, we fix a Riemannian metric on M alpha, and we identify EIX with R, so isometric. And we will only care about absolute values, so really what's the orientation here is quite irrelevant. And what we want is to bound this number. So the lemma then said for every epsilon positive there exists a set L, mu of L larger than 1 minus epsilon, and constant C positive such that if x is in L, alpha t of x belongs to L as well, and t is in the kernel of chi I, but other than that it could be huge, then absolute value of alpha xi of t is between z and 1 over c. So it's uniformly bounded. Whenever you start in the set L and you end in the set L. So this is what allows us to fly along the kernel and return from the leaf, the wi leaf of x to the wi leaf of x, and do it with ergodis, so with mapping the measure affinely to the measure, so that you can take a limit. So when I can do it here. So then when I take this sequence and working a little bit, managing to make all these guys in L, and I even restrict a little bit more, I get So that this is a normal family, so we have convergent subsequences, and this any subsequence will have that. So I can take the limit here into some g infinity, which will map this into this, that in coordinates will be affine, and it will map g infinity star mu xi will be proportional to mu ix. And that's what we were looking for. And essentially this plus whatever ergodicity trick we already used at some point, I can get any y essentially in this manifold taken with respect to the conditional measure. And that's, once we have this, we pretty much. Okay, so I will still discuss a little bit this end of the argument, but the whole point is in this arrow, why I can do this, and is because of the lemma. So this tells me that I can take a subsequence. Okay, so proof of the lemma. So we let L1 is such that mu of L1 is larger than 1 minus epsilon square. So it's very, very large. We are giving some room there. And x into mu xi x into wi alpha x into hi x, and I guess, well, this is included here, but let me just put it. All these guys are continuous. On L1. Okay? Then L will be L1 intersected with some other guy, which will have also measure larger than 1 minus epsilon square, and then the intersection will be measure at least 1 minus epsilon, assuming epsilon is really small here. Maybe I need to intersect with someone more guy. So, so this guarantees me all continuity properties of these guys. So, as I said, I'm making this identification, so I'm using this Riemannian metric to make this computation. Okay, so we are good now. So I need a following sublemma. Who says as follows. So there exists, or even take the set of points x in M alpha such that h of the ball centered, actually, okay. Second. Yes, that would be good enough. R, for every R, we take this set R naught, where H is the semiconjugacy and BIR is contained in W I alpha X is the ball of radius R. Okay, measure with that Riemannian metric. Actually, any other Riemannian metric will do the job because I'm just asking here positivity, so I'm not looking for any estimate here. And I wanted to say one more thing, and I could even think of it through the HI coordinate i's, and will do as well, so it really doesn't matter much. I could just say for every open set containing X, this any open connected set inside the WIX, which is a one-dimensional manifold, the image is not a point, and that will be do as well. It's a topological statement. So even though it looks very geometric because there is a length here and there is an arc here, it's a purely topological statement. Okay, but I still didn't say anything. I define a set. I have to say something about this set, and the statement is that mu of R naught is not 0, 1. So almost every point does it. Now the proof. We have that alpha t compose H is rho of t compose H, and this implies that alpha t of R is R naught for every t. So it's an invariant set because having this positive length is an invariant by rho, and the interaction of H and rho gives me that, and the for every R makes the game. So this implies that either mu of R naught is positive, is 1, or mu of R naught is 0, because we assume the measure is ergodic. So it's either full or zero measure, and we have to rule out the guy being zero measure. We just need to find a point where this measure is non-trivial. Okay? Just as soon as for one point this is true, well, 1 point, a set of positive measure of points, but this means taking at random 1 point. Or if you want, we can assume by contradiction that this set has measure 0. Okay, now so let R1 be the set of point X in M alpha such that the length of H of W by alpha of X is positive. So now I'm mapping the whole business. And we have again 0 or 1 because of ergodicity and invariance. And my first claim is that these two sets measure the same. So if one has zero measure, then the other will have zero measure. And the reason for that is the following. So for every R positive and for almost every X, take T1 such that chi of T1 is positive, so a guy that expands this business, and we have that W is equal to the union with k positive of alpha k T1 of this B I R alpha in alpha kt1 minus t1 of x. And this is just saying that when I take 2 points in this guy and I iterate them backward, they are asymptotic. So at some point, their distance is smaller than r and stays smaller than r, actually, but it doesn't matter the fact that they stay, I just need the union. So at some point the distance is smaller than r. Doesn't matter how far they are, at some point this is true. And this is true for almost every x by Pessin theory and this characterization of this Wi manifold as the intersection of possible unstables. So that's why this is good for any T1 making this positive. Now this states, this plus the invariance is telling me that if this set has positive measure, well, certainly this containment is trivial. So if this set has positive measure, then this set has positive measure. But on the other hand, if this set has positive measure, then this guy has positive length for points. So the image of this guy has positive length. But then by this union, it tells me that for this guy, so no matter who is the R, I take this point X where this has positive guy, so I get a positive set of points where this is positive, and then I'm done. Okay, so it's just some very basic writing. So which means that if this set R0 has zero measure, then R1 will have zero measure. So then what I'm facing is full collapsing of these Wi manifolds. Okay. Now, this will completely kill the contribution of entropy coming from this Wi manifold. That's in the entropy type of bound. The other will be the geometric bound. So let me write down the geometric picture behind this. So, okay, this finished proof of lemma 2. So now we prove no, this doesn't finish yet proof of lemma 2. Wait a second. This is just telling me. So now let us show mu of R1 is 1. So by contradiction, let us assume mu of R1 equals to 0. Then for mu almost every x, the length of, actually more than the length, just directly, h of Wi alpha of x is just h of x. So it completely kills everything because length 0 means a point. It's a connected set. Okay, I don't want to do that. Let's go here and let's go here. So now we do the geometric picture. We have done at some point. So let me do it easy. So take t such that chi I of t is positive and chi j of t is negative for every j different from pi. Okay, and I can do this choice because I know I can make whatever choice I want. Now I take here the stable manifold of t for the point x, local, and then I take all these unstable manifolds for points y. Okay. So this is the alpha picture. So alpha. And now I map this into here. Now this set, which I call it lambda, which let me write it now, is epsilon of the tail. So this is the union, so it's all the union of this of y. Y belongs in some Pessin set and y belongs to some epsilon naught ball of some point x naught. Okay, there is the point x naught, there is y, and here is what we are taking. This I can intersect actually with this set R1, R1 complement. Wait a second. So I'm assuming yeah, so R1 complement. So R1 has zero measure, so the complement of R1, which is the set of collapsing of Wi, has full measure. So this set intersecting with this set has no implication essentially for the measure point of view, but it's very important for the topological reasons. Now, the big comment here is that this, so the two observations in orders are that this guy is the W1, the Wi alpha, the local guy. So that's the first, because of the choices. So all the other directions are negative. The second observation, and that's why I draw the stable, is this WUT log of y intersecting on the WST log of x naught is non-empty for every y in this set lambda. That's why I want the guy in a Pessin set, which exactly means that these guys are long enough so that they will intersect. And the final observation is that mu of lambda is positive. And this is true for the correct choice of x naught and Pessin set. This will be true. And actually it's the same as the set lambda. Now with these three observations, now what we get on the other hand, I take h of lambda, the Lebesgue measure of h of lambda has to be positive, because mu of lambda is positive, and the measures are one sent to the other. But h of lambda is contained in h of the stable manifold of x naught for this value of t. And the reason for this is exactly this union. So I take any point here. The point here in lambda belongs to R1 complement, and it also belongs to the W1 of some point. Now this W1 will intersect the stable manifold, and I know the whole W1 is collapsed. So which means that h of, okay, so for this, we take y in lambda, take z equals to the intersection of this, so this intersecting point, w t log of y inter ws t log of x naught, and hence, since y belongs to R1 complement, h of y is h of c. Because everything is collapsed. And hence, h of c belongs to this guy here. So, h of lambda is inside here. But this guy is contained in plus the stable space for this t, which has 0 measure. And that's a contradiction. Okay, so it's pretty much the same type of contradiction, which was the geometric contradiction for the fact that the Lyapunov exponents are resonant upstairs and downstairs. Okay.
How do you do this third observation that if the new measure of lambda is...
Okay, let me see. I hope I did it right. So we have, by definition, essentially, lambda of A is mu of h minus 1 of A for every A in TD, or in M rho actually, because we are doing it, but it's not much of a problem. We are doing it in the suspension, but it's pretty much the same. Yeah, I'm drawing this, so I should add the orbit foliation. So everything here is perpendicular to the orbit foliation. So I'm doing the argument in TD actually, but it's pretty much the same. Okay.
But A should be downstairs, no?
Yeah, A is downstairs. It's in the linear, so A is in the linear guy. Yes, yes, yes. Now we apply for h of lambda. Now, why h of lambda is measurable? Well, you may need to do some argument, but you just, h is a continuous map. Just pick any compact set inside lambda, and we are going to show this for any compact set inside lambda, and that will be good enough. So, and h of compact is compact. So this is not a problem. Or you can even use outer measures for that matter. So this wouldn't make much of the problem. But then you apply this to this. So this is mu of and this contains lambda, so this is larger than mu of lambda. So if this is positive, this is positive. Since we are going to get a contradiction, so there is no problem to use outer measures here, you see? So even you have, using outer measures, I don't need to discuss whether the h of lambda is measurable or not. Still, you will get lambda. The outer measure of this set is positive, but topologically, this set is inside this guy, and whoever is inside here has outer measure 0. So you get a contradiction, and then you don't need to care. But if not, you just use compact sets. Okay. So we got that this set R1 is full measure by contradiction, and so the WI manifolds are not collapsed, which is reasonable. So that's always the case, actually. So the stable mass manifold cannot be all collapsed. And then ergodicity will tell you that I've never collapsed. And this tells you that these guys are never locally collapsed. Okay, now next two statements, which are pretty much so.
Yeah, I guess this claim that mu of R1 equals mu of R0 also covers the other way around estimate.
Yeah.
So.
Yeah. Okay, now, yeah, actually. Next lemma is set R2. Now I'm worried not about fully collapsing, but a full explosion, which is impossible, but I have to state it. So R2 is the set of X in M alpha such that the length of Wi alpha X, oops, again I need X alpha is infinite for some R positive. I don't want this length to be infinite. Okay. Now, and again, the game is that okay. Now, this actually again R2 will be invariant, so it's either 0 or infinite mesh or 1 or measure 1. But more important than that, it's really why it's not everything is because the Wi manifold is not defined everywhere. But as soon as it is defined, you will have these lengths being bounded. So the proof is take X such that Wi is defined. Okay, fine, you're right. If not, I should put measure 0. Yeah. So then is for every, yeah. Yeah, so. Yeah, I was right in the complement. You're right. So you take these guys so that this is defined, then this is compact. And is contained in Wi alpha X, hence H of Bi R is contained in Hx closer plus Ei and is compact. And so you are compact in this line, and a compact interval in this line has finite length. That's it. So why it has full measure? Because the points where this is defined has full measure. And that's all I need to know. Okay, once I have this set R0 and this set R2 with full measure, then we intersect these two guys, and it's still a set of full measure. And this gives me the next set. Is equal, maybe let me put AB. Actually, we could just put one parameter. Yeah, let's put just one parameter. Is equal to set points in N alpha such that the length of B, I need a second parameter. Okay, now it should be okay. This is less than 1 over a, larger than a, and I want this for wait a second. So I said there for every r this is true. So then yeah, let's just one parameter is good enough. So you fix one r naught and take this. And the claim is that the union of Ka a positive smaller than 1, because I'm assuming a is smaller than 1. This is well, this is larger because I'm only caring about the size r naught. So, and r naught is whatever size is fixed. It's really quite irrelevant, the size r naught. So could take r naught equals to 1 will do. Good, I hope. But if you want, maybe just for future use, let's keep it for every r naught. You contain this, and then this means that for every r naught, there exists an a that depends on r naught, such that, and for every so this guy depends on this r naught and this epsilon, such that mu of k a r naught is larger than 1 minus epsilon square. So I can pick this guy also with huge measure. And then I take the previous Lusin set intersected with this guy. Good. Now this should do the work. Okay? So So let's see. So let's see what we want. I start with a point x here. I have alpha t of x, the iterate of the guy, both belonging to the same set, which is the relevant set. Now I look things in coordinates, so where should I put it? Yeah, I should put it here. Here is hi x, here is hi alpha t of x. The measure will be irrelevant, so actually almost everything is irrelevant. So this map here is what we call multiplication by alpha xi of t, and it's this number that we want to bound. Okay. Now I have this map h here and here. This map into hx plus ei, and this maps into hx, h alpha t of x plus ei, and this is rho of t. But rho of t is 1, because I'm taking t in the kernel of chi pi. So this is an isometry. It's actually, if I use the hi accordingly, here is just this map is identification of this AI with this other AI. And this diagram commute, which means that H of alpha x, okay, I should be more careful. H compose hxi compose alpha xt.
Then it should be alpha of t of x.
Yes, because yeah, I'm doing this, then I'm doing this. Yes, completely right. This is equal to h compose hi of x. And actually, what I care, and let me do it with epsilon of detail. So because this equality is due to some identification here of this, so there is a rho t happening, but I only care about, as I said, this guy being an isometry. So let me just be epsilon more explicit here. The absolute value of this, which is the difference on when I take 2 points here, I map them all the way onto here, and I look at the difference of these 2 points. This is exactly the same as h compose hxi of b2. Okay. So that's what I know, and this is for every pair of points b1 and b2. So that's exactly what I know. Now let's call this guy here G. Let's call this guy here F. Let's call this number lambda. Okay, so what do we have here? Let me just do the abstract calculus lemma. So we have that G of lambda b1 minus G of lambda b2 is equals to F of b1 minus F of b2 for every b1, b2, and essentially in R. So now I just do my identification with R. That's what we have. And what I want is a bound on lambda, depending on properties of G and on F. Okay, and the point is that the only thing I know about G and F is continuity properties. Okay, so remember G here is H compose H alpha t of xi, F is H compose hxi. So H is continuous, it's uniformly continuous, it's beautiful fixed, doesn't depend on anything. So it's not a homeo, but it's continuous. Now hxi's are C1 maps, but they depend on the point x. Now the good news is that I ask both x and alpha tx to belong to some set of continuity, so the derivative of hi's and the uniform continuity of hi are very well controlled here. Okay, so now let's see the picture. I take my point x, I take this BR naught ball I alpha of x, and I know that this guy is a compact set, so the H and the HX are uniformly continuous on this guy. It's compact set. And actually, when I say uniformly continuous, I will be more explicit in a second. I will want it to be uniformly continuous where the uniformity is in X. And that will be important. But I will discuss it later.
But wait, so HI is measurable in X, no? In the beginning.
HI is measurable, but remember I took this set L.
Yes, you're taking a Lusin set, but how do you know that the Lusin set that you took it includes this one?
Because X belongs there.
Yes, but
So
it's
it's
a closed set.
no. Okay, very good point. So that's good. I'm happy you addressed that. Because this is a very important part on this use of pacing theory. Okay, it's crucial. So the map is from X into immersions or embeddings of, let me just put directly R into N. So this is a measurable map. Now, when I take a continuity point, or a Lusin set of continuity, actually, typically one says Lusin set of continuity, while what people really mean is the very basic of the proof of Lusin. You just want to have some bounded norms here, okay? But for that matter, it's the same. So, which means that the C1 norm as an element here is bounded. On the whole domain of this map. Okay, actually the domain of this map is not even in the manifold, so you cannot even talk about measures, even though we know we are doing it, so, and we do it all the time. We have the measure on the manifold, we take conditionals, and then we bring it into R. But the truth is that this C1 norm is less than C0, which means that HXI of B minus HXI of W is less than C0 B minus W. And of course, well, what is the topology here? Since the domain is not compact, then this topology is about convergence of compact sets. So this C0 will happen only on some, say, minus NN, so you fix some interval, you have this uniformity there. Okay, so this will not happen always, but will happen on this compact. And that's what I'm doing here. So whenever I take 2 points here, they will not separate. Okay, good. Now, this is very important.
The point is that the C1 bound comes from essential pacing theory.
Yes.
Okay.
So yeah, it's not that this guy, so the variable x is not a variable where you are evaluating your diffeo, it's the parameter where which these diffeos are moving. Now this map F is mapping this interval into something. Yes. Now this something I know that has lengths between A and 1 over A. So this cannot be too large, not too small. Okay? The uniform continuity tells me the same thing here. Okay, that is not too large and not too small. Actually, not too large is by uniform continuity. Not too small is actually because I know, because a uniformly continuous function could collapse everything. Now, the important part of the game is I apply now my alpha, so my multiplication by lambda, and then the g. This maps into this set b lambda r naught I. I apply the g here, and I get the very same interval. So it's a copy of this, which is between a and 1 over a. Now, if this lambda were too large, this interval will have to be too large. Or if you want, let me do it in the easy case first, and let me show that lambda cannot be too small. So if lambda were too small, then this interval would be too small. And if interval is too small, then the uniform continuity will tell me that the image here is too small, contradicting that it was large here. Okay? And what the smallness or the largeness, it just depends on continuity properties of this f and this g. And actually more than of f, continuity properties of this g here and the value of a happening here. And in this case, these are the only two things I care. So, so this equality here is telling me that this length is this length, and not only in the broad situation, but any 2 points, when I take them here or I take them here, is the same. So this essentially will give me that the lambda is larger than 1 over c. I just consume all my time. So you can really do very explicit the value of c in terms of the epsilon delta continuity properties of here, epsilon r naught, delta a, or something like that. So it's very, very explicit. Now, why lambda also will have to be smaller than a constant c? Essentially, you go the other way around. You just apply the very same thing we just proved. Instead for t, for minus t, and then instead for the point x, for the point alpha t of x. And then in the case lambda were too large, then when you take the inverse, lambda will be too small. So then instead of taking this set R naught, you will be taking a much, so this will be a small set. We will take lambda minus 1 here and the R naught here. And then it's the same. Now you use the uniform continuity here, and you use the largeness here. And then you are done. So that's pretty much it is. So time's up. So let me do it on Wednesday. Let me go again through this picture just to make sure we all got it, because it's a very important statement. And after that, I show how to finish the absolute continuity. Okay, thanks. Yeah, should be okay. So I want to repeat what I did last time and actually show you one type of argument that will not work, but it works seeing why. So it's something that I'll ask it before. So, but yeah, let's go through it. So let me show you the picture of what we were doing. I will make the assumptions so that the picture works. So they have, these assumptions are about the choice of the Lusin set we were discussing. So I will not go through that again, but yes, through the picture. So, so we have this map here alpha of t. So this is wi of x, this is wi of alpha t of x. We have these coordinates here, which is this hxi and eix, which we had it identified with r. We have here ai with alpha t of x, which also is as well identified with r. And we have this map, which in these coordinates is just multiplication by a number, which we call alpha xi of t. And all this discussion is about how to bound this guy from above and from below with some sort of uniformity. Of course, we are taking t in the kernel of chi I. Let's put this a little bit further. T in the kernel of chi I. And we have the conjugacy H, which is a fixed Hölder continuous conjugacy independent of points and anything, which will be mapping this guy into h of x plus ei. We have here rho of t, which is identity, or it's rho of t so far, which maps into h of alpha t of x plus ei. And my point is that you have some natural identification here, which makes this identity. And these natural identifications are mapping 0 into h of x, and here 0 into h of alpha t of x, which is nothing but rho t of h of x. And this is just really identity because of this choice. And we have h here. And all this picture commutes. Now the game is as follows. So I will try to clean up all this huge amount of spaces we have. So we are calling this number lambda. We are calling this composition here G, I guess. And we are calling this composition here, well, a little bit more actually, F is this composition with the inverses of this, so that we are really going to the reals. But, okay. These are really very naive and trivial isometries. So the equation becomes then G of lambda v equals to f of b. Okay, and
You also have alpha, no? Oh, yes.
yeah, we call it a lambda. Yeah. We also have that f of 0 equals to g of 0 equals to 0, which really doesn't matter because f of 0 is equal to g of 0, and then making it 0 or any other number is up to a constant, so it wouldn't affect lambda. So this is not important. Now, this formula comes with this picture. Interchange, maybe, yes. We apply lambda and then f. This is the same as g. Yes. Yeah, we are actually going to do both. But yeah. Yeah, and yeah, that's the game that will make everything work, is that I can put the lambda here or the lambda inverse here. And in one way I will bound lambda, and the other way I will bound lambda inverse. But let's bound lambda now. So we have this map, which is multiplication by lambda, we have this map F, oops, this map G, and this map F, and both do the same thing. Now, G and F will be uniformly continuous with some uniform bounds on the interval of length 0, 1, say, or some fixed R0 length. Also, I know that this interval here cannot be collapsed too much. Okay, so I have this B0 or BR0 of 0 interval here, and I will know that the length of G is larger than some number A, which is fixed. Now I know that given epsilon positive, there exists a delta positive such that if the length of an interval is smaller than delta, then the length of f of the interval is smaller than epsilon. Now we take actually delta sub A with respect to here, so actually let's do it directly. For this is the same A. And then the claim is that if lambda times R0 were less than this delta A, then f of lambda of the ball BR0 0 and okay 2 times because the ball is centered, so doesn't really matter. So this guy here will be smaller than A by the uniform continuity, but this is equal to G of the ball here, which is larger than A. Okay, contradiction. So this implies that this if, so lambda is larger than delta naught over 2 R naught. And there is a lower bound for lambda. So lambda cannot be too small. How much is the bound? Is this delta A from uniform continuity of the F, the R naught, which is the guy that is not collapsed more than A. The delta also depends on the A, so here the A is a very important number. The 2 is a 2, so who cares about 2? But what is important is that it only depends on uniform continuity properties of this map F down here. And remember, this map F is H composed, wait a second, this way, H alpha T of X I. So this is F. Now this is uniformly continuous. This guy, you make it belong to a Lusin set, and then by belonging to a Lusin set, you can ask for the Lipschitz constant of this guy restricted to this R0 ball around 0 to be less than some C0 number by belonging to this Lusin set. So as you want the measure of the Lusin set to be larger, this C guy here will be even larger, but it will be fixed. Now, once you have this Lipschitz constant fixed, then the uniform continuity of this will be essentially this C epsilon times whatever uniform continuity coming from H, which is Helder continuous, so you can even go and do it very explicit how this delta A depends on A. Now, about the R naught, well, again, you go to these Lusin sets and you get how this R naught and this A are attached one to each other. And this you have almost no control because you just know there is some non-collapsing. But that's it. So this argument shows that lambda is bounded below. Now, how to bound it above? Okay, so how to bound it above was exactly what what Alp said. I can write as well this formula because it will hold as well this way, that f of b is g of lambda inverse b. Okay, now the roles of f and g will be reversed. I want G to have non-collapsing, F to have non-collapsing, and G to have uniform continuity properties. And that's why we needed to assume that both X and alpha T of X belong to the Lusin set. Okay? And then in this way, you bound lambda inverse from below. And once lambda inverse are bounded from below, you are done. Now, what would be a different way of bounding this lambda? Trying to do the same picture. So the game here was that the problem was that we have this interval and this became too small, lambda small. And then uniform continuity will tell us that this image will be also too small, and then you won. Now, if lambda were too large, then you will have a huge interval here. Then you will try to argue that this interval, which is huge, cannot be collapsed into something which has mid-size. Okay? But this is hard to do because this interval is too large. So the typical way of arguing here will not be too successful. The typical way of arguing here will be to chop this huge guy into integer part of lambda intervals of length 1, and then try to argue to each of these intervals is not collapsed here, and they are disjoint, and then they will be too long. But disjointness is not at all obvious. Even non-collapsing is not at all obvious because the non-collapsing we only know on a set of very large measure, and we don't know how this set of large measure hits this long interval. So it could hit in an atom. So maybe only one of these guys is not collapsed and all the others are collapsed. So really we lose a lot of control there. That's why you don't go into this large picture, you just keep in the small picture and do the argument, the symmetric argument, and that's it. Okay, so that is how we control lambda. And so the main business here is that we can control lambda. And now let's discuss the end game of the rigidity. So we define this G X as be all the transformation T from EIX to EIX such that T affine and T star mu bar IX is and the main lemma is the same as in the linear situation that claims that the mu bar xi of the G orbit of 0, so this is the complement of this, is 0, or Gx0 is the P of 0 such that Gx is oops, this is gx. So, okay, anyway. So the proof of this proof is same as linear case, but using that so this bound if x and alpha t of x is in this Lusin set. Okay, so this is for almost every x. So what I say same is almost same. So one big difference, if you want to call it big, is that in the linear case, when we take these iterates, these numbers were always 1, and now we don't have them being 1. We have them bounded. And so in the limit, you have an affine map, not an isometry. Okay? That's why I'm putting here affine and not isometry. So in the linear, I think I also put affine, but it was thinking on this situation rather than thinking on the linear. In the linear, I can always put isometry, and there is no problem with that. Okay. Let me think one more thing. Should I say something else? So yeah, I think that I don't need to add much more because we already went through that. We don't want to repeat things many times the same argument. So to make your life simpler, you do as always. You use ergodicity and show that the set of points doing this is either full measure or zero measure. That's quite easy because this group Gx, you can see that Gx is essentially alpha xti Gx G alpha t of x 1 over alpha xi t or something like that. So you conjugate by this and you get one from the other, and so the measures are also the same type of invariance. So you get that the orbit of 0 is mapped into the orbit of 0, and so either both have 0 measure or both have don't have 0 measure. So so this gives you the invariance. So you only care of showing that this high has positive measure, the set of points doing that, and then you pick your Lusin set of larger than 1/2 or 3/4 or something close enough to 1, so that whenever you have the 2 points there, then you will have this bound here, and then you do the pi partition trick to show that you have ergodicity on the kernel along this alpha I, so you have returns to this region with the frequency you need, and hence you can reach this game where you have your x here, you have your y here, you iterate along the kernel, you can come back here without problem. while you stay in this set LC. So you started with the point X in LC, you take the iterates T, alpha T belonging to the iterate and approaching this Y. So in the limit, you get this transformation, which is affine, sending the measure to a multiple of the measure. You also want this set LC not only to satisfy this, but also continuity of these conditional measures and continuity of the WI manifolds and of the EI manifolds. And so you get this transformation T. Okay. I still want to say one more thing, which is important, but because this is proving a little bit more, and that's very important, and is where actually rigidity start to get enhanced. So, but before saying that more thing, let me just almost finish it. So after we know this, then the end is really exactly the same as the linear. So with the appropriate lemma. So you have this group, you have this measure. Since you have entropy, and this comes from because the entropy considerations are well settled here, this measure is not atomic, and hence this group is not atomic. Now it is a group of affine maps, so it's not just a group of translations, but still the standard result that says that if you have a measure which is invariant by a continuous group of affine maps, then the measure is nice, is still okay. So you need to say something else, because if you only had dilations, then your group of, so your delta at 0 will be invariant by this group of dilations. So it's really about how is this orbit being non-trivial rather than just the group being non-trivial. Okay, that's why you really care about this orbit being non-trivial. That's just some very basic measure theory statement that let me write it here in abstract because it's a nice statement abstractly. So, which is let G be a subgroup of affines of R, mu sub naught locally finite measure on R, and assume mu naught is not atomic, and actually I could rephrase it and make G depend on mu naught, but it's the same. Q star mu naught is equivalent to mu naught, for every t in G, and the second is this mu naught of the orbit of 0 complement is 0, then mu naught is absolutely continuous. And actually not just absolutely continuous, mu naught is of the form e to the for some beta. Maybe some, it's up to a constant is this. So d mu naught is this question. Okay, and then afterwards you show that beta has to be 1, and so you are really having dt. But that's really very easy to settle. So I leave it for you. Okay. So what I wanted to say. Let me go back here now. Into this argument and into this picture. Okay? Because this argument essentially is telling you that the measure mu is absolutely continuous along the wi direction, then this implies that is absolutely continuous along all the wi's, because the wi's was chosen any I. So you have absolutely continuous along all the direction, and then standard Lebesgue-Young will tell you that one way or another the measure is absolutely continuous. So one way is that Pessin entropy formula holds. Other way is just you go to Lebesgue-Young and they show you that under this huge amount of absolute continuities, you get that the measure is absolutely continuous, and then you don't have any problem. So this settles the Kalinin-Katok theorem. But as I'm trying to say, Kalinin-Katok theorem tells you more than just this. So Kalinin-Katok theorem will tell you something about H. So H by now is sending Lebesgue measure to Lebesgue measure, or maybe not Lebesgue measure, it's an absolutely continuous measure into Lebesgue measure. But I can say a little bit more, which is that the semiconjugacy H is smooth along the wi directions. Okay? And let's see how this is already shown in our picture.
Before you go on to that,
Yeah.
can it happen that G sub x of 0 is actually not equal to R instead of having full measure?
At the end of the day, no. So at the end of the day, Gx of 0 will be equal to R. But what you can prove in principle is just this property. So after you know this, then you show all the other statements, then it will hold that it is actually equal to R. But it is only afterwards. And there are two ways of proving that. One is very specific of these higher rank actions and situation, because then, as I had down here, then is even in this abstract lemma, after I know that the measure is like that, then I can prove that the orbit of 0 is all R. So by maybe slightly switching the group G, so we do G mu naught, which is all the T's, such that T star mu naught. And then under this, you will have that G mu naught of 0 is R, after I know what is mu naught. But from a dynamic point of view, without having this higher rank business, it follows from Lebesgue-Young that once the measure is absolutely continuous, then it is Lebesgue hard measure along this R. Okay? And really, there is two measures which are the same, but one really have to call them differently. One is Lebesgue measure, the other is hard measure. Okay? Lebesgue measure comes from geometry, hard measure comes from group theory. So, and they end up being the same for multiple reasons, but here being hard measure has to do with some group structure coming into your space, not just from some geometric structure coming into your space. So when we call wi of x and we take this parametrization, this very specific parametrization hxi, we are given an affine structure here. Now, this is giving you some identification of this manifold with R. And once I identify this with R, then I have dt, and dt is hard measure in R. So it's not any absolutely continuous measure, it's a very specific one, which is called dt, which is compatible with the group's multiplicative and additive group structure on the line. So this is why I'm getting really dt without holes and without nothing. And that's true always in dynamics. Okay, so whenever I have some nice Wi manifold foliation coming from pacing theory with some axiomatic assumptions. In the nicest situation, let's just assume is the unstable foliation. And the conditional measures are absolutely continuous. In these coordinates, which exist always, as soon as you have this unstable foliation, the measure becomes hard measure on this manifold. Okay, so the dynamics become linear, or if you are not in one dimension, they have some sort of normal form, but the measure is always hard measure. Hard measure without holes. So this implies that the group then of translations leaving this measure invariant is everything, because that's what hard measure does. Okay, that's very important. Now let me go back to that picture. I will draw it again here. Sure. I have x here, I have y here, and I have this recurrence business in the kernel of chi I, and such a way that alpha t of x belongs to some Lusin set, x belongs to some Lusin set, this mu of L is very large and is a sequence of guys doing this job, and you have some convergence and the measure to the measure and blah, blah, blah. Okay? Now, while I do this job, I can just go and look what happens for the linear. I take actually h of x here, h of y here. I take rho of t. The very same rho of t. And here will be h of alpha t of x, which is rho t of h of x. Now here is life is much simpler because this is an isometry. Everything varies continuously. Everything is really very fine. Conditional measures are hard measure because it's lebesgue measure. So really, any convergence analysis here is almost trivial. But then, by doing this argument, I found t sub xy, which mapped EIX to EIX, affine, that mapped txy of 0 into hxi inverse of y. So it did this translation. It sent the measure to the measure. Now really sending the measure to the measure is not so relevant. So it is secondary. And while I was taking the limit here, I could have been taking the limit here. And by taking the limit here, certainly I would be founding some t hat xy from the space EI to EI that is mapping. So this is an isometry, because on this side of the world things are isometries, and t hat xi of 0, because I'm identifying this guy, is h of y minus h of x, which is this distance. But since I'm doing the things simultaneously, when I'm taking h, compose hxi, okay, so the way I'm building this txi is, maybe let me be a little bit more concise. So I'm taking h alpha t of x I, compose this inverse, compose h xi. Okay, so this is the guy that is conversing to Txi. That's how I build this guy. Now,
It should be the other way around.
no, I think it's correct because Hxi goes from the linear space into the manifold. Alpha t brings you from the manifold to the manifold, but switching from this point to this point. This other point brings you back. So this guy here goes from Eix into Ei of alpha t of x. And then this alpha t of x goes to y. Then, yeah, there is, but you are right, there is some missing guy here, and this is very important. There is a composition, but the composition is taken in the limit with h, because I have to go back to hx, because if not, this just is going into the y guy. So I have to do h, and then I do this change of coordinates from the parameterization in y to back to the parameterization. That's why it's an affine map. So this is the affine part, the translational part. So the nonlinear part, this is purely linear. And this is the translational part. Very good. So this is the guy which, well, actually, it is a problem because this composition here is not 100% well defined if I do it this way, because this guy goes from the manifold to the space Ei alpha t of x, while this guy goes from the Ei of y into the manifold. And then these domains and codomains here do not intersect. So this is only an approximation type of what's going on. So it is better written, actually, for that matter, in purely nonlinear terms. So you have this alpha t looked from alpha I x into wi. Okay, and just have in mind that in linear coordinates, in affine coordinates, this will be conversion. And now the point is that when I have this h compose alpha t, this being rho t compose h, this will imply that when I come here, I take a point here in Ei of x, I map it into the Wix, and I map it through h. Okay, now let me, oops, sorry, let's go back again. So I first take a point here, I apply the Txy, I apply the Hxi, and I apply it to h. This will be the same as taking this t hat xy here, applying h, and then of course I will still have the hxi here. Okay? So this, let me write it here back, this lemma so I get that h compose says that for mu almost every x and for mu xi without the bar, almost every y in W I of x, there exists Txy affine also T hat xy from EI to EI, actually hx, hy, and this T hat, I have it very, very explicitly, is B plus hy minus hx. So it should be send 0 to hy minus hx, so this is correct, such that h compose hxi compose Txy is compose the same guy. Good. Now what this is telling us? I have this group of affine maps here. So it's not the same group as before, it's not even a group so far, it's a family of affine maps, let me say, which are the affine maps that I build this way, that I build by taking these t's on the kernel and doing this argument of going to the limit. Okay? So the group we discussed before is a little bit larger than this. So we just use this technique to show that there are a lot of elements in that group. But that group could be even larger. Because actually, this other group allows some expansions, which we don't care. But they may be there. Here, we are not putting them. We could put them. So it's really not much of a difference. But we have this family of affine maps, which we know they act transitively because we can move x to any other point, or almost any other point here. But it's almost any other point with respect to lebesgue, because we already know that the conditional measure is lebesgue here. And we know that when we do this job, here we get translations, the corresponding translation. And we have this map here, which is intertwining this affine structure here with this translation structure here. So the corollary is H compose HXI is affine. Okay, and it's an affine map. Let me just emphasize here from EIX, which has a vector space structure, which we typically identify with R, into AI. So this map is an affine map. And this just follows from here plus very basic formulas. So if you have a continuous map that sends affine maps to affine maps, and the amount of affine map here is transitive on the reals, then the map has to be affine. Not only that, this shows also that by these carefully chosen guys, I really can make this Txy isometric. But for this, I need to make some normalization, so I don't want to enter into that. Because what I really want to do now is, what's the use of having this guy affine, is that this guy is affine, Hxi is a smooth diffeomorphism. This means that H is a smooth map. So H was only Hölder continuous. We were discussing whether it was collapsing, it was not collapsing, how this uniform continuity, so the corollary of the corollary is, yeah, it's as smooth as the HXI. So H from WIX into EI, or H of X plus EI, to be more precise now. So here I also made, so there is a composition I didn't make here, which is removing the H of X to bring things to E. Now I'm doing it explicitly here, is a diffeomorphism as smooth as HXI.
Which in turn is as smooth as action.
Exactly, absolutely. So if the action is infinity, this is a infinity diffeomorphism. And it's a diffeo, so there is no collapsing at all. It's injective. Okay, it's one-to-one. So the intervals are mapped into intervals of pretty much the same length if you put the correct Riemannian metric after all, but that's useless. So this is a huge source of rigidity because now H being a diffeo on these WIs, if I have a little bit more of information, I could end up, and that's how you do it, showing that H is actually a smooth diffeo everywhere. But for this, you need more uniformity. You need the WIX to exist everywhere. And we already know that the WIX exists almost everywhere. So in this general framework, that's the best you can do. Well, you can do a little bit better. Let me just state it. The ultimate sort of theorem you can prove, just pushing a little bit more on this. Direction, which is that there exists a set R. Now I come back to TD of full measure such that for every X in R, for every T in ZD minus 1, H from the unstable for this element to X into H of X plus, so assume alpha is CR, R larger than 1, so is a CR diffeo. Moreover, for every epsilon positive,
We need more than one R?
yes, strictly larger than 1. Yeah, at least C1 plus epsilon. Moreover, for every epsilon positive, there exists K epsilon on TD mu larger than 1 minus epsilon and CR diffeo H epsilon from TD to TD such that H epsilon restricted to K epsilon equals to H restricted to K epsilon. So that's essentially how far you can push this up. It's mostly essentially analysis after you have what is written there. So when you restrict to the unstables, it is a smooth diffeo. Globally on the manifold, it may fail to be a diffeo, but if you restrict to set of very large measure, then it coincides with a global diffeom. Okay? So in the complement of K epsilon will be different, so you have to make modifications so that it is everywhere a diffeom. So let me show you the picture of what this second part is telling you. And we finish for today. We essentially finish with this. Kalinin-Katok. There are a couple more things to do, but we better move on. So what this is meaning, imagine that this is a torus. I'm just drawing in the case of 2 dimensions. Now you are given, so you have this set K epsilon, and the H is mapping this set K epsilon into a set which also will have large measure because we know what happens with the measures. Now, on this dust set, I have H epsilon being equal to H. And now H epsilon is a global diffeom. H is not a global diffeom. H can do collapsing, it can do some nasty stuff.
What does this mean? Outside this K epsilon, H epsilon is not a conjugacy?
Exactly. Outside is not a conjugacy. Yes. Absolutely. So if the point belongs to a K epsilon and the image of the point by alpha is in K epsilon, then you will have the conjugacy property. But if either of the point is not in the K epsilon, then you stop having the conjugacy property. Or you maybe you are lucky and it happened. It's very unlikely. Okay, I guess that's it for today. My idea for Friday and next week is to state Zimmer amenable reduction. So we are switching from these abelian actions and this measure rigidity to still something which has some flavor of rigidity, but it's some fact about groups. And it's a sort of different proof of Oseledets theorem, which is due to Zimmer. And then I hope to end the course giving some ideas, at least, of what is Zimmer cocycle superrigidity and relations with Margulis cocycle superrigidity. Okay, so I guess that's it. So we'll see you on Friday. Thanks for being here. Bye-bye. So yeah, in any event, just to finish before I start with the other, realistic models of Bernoulli on any manifold, even on any surface. Well, on any surface, I guess one can do what is not trivially known. I'm not sure one can do, actually. I'm not sure. No, yeah. Bernoulli on any, I think realistic Bernoulli on any surface can be done, but not necessarily on every homotopy class. So that's less trivial. So homotopic to identity on a surface, that I don't know how to do. Even on the torus T2, homotopic to identity. I'm not sure I know how to. That's a very good point. It will be good to do it. Okay, let's go. So we are going to discuss, as I said, today and next week, Zimmer's amenable reduction. So it goes much beyond Oseledets theorem. One can deduce Oseledets theorem as a corollary of this plus Birkhoff-Ergodic theorem, but the proof is completely different, so it follows different ideas. There is actually in the theory of Oseledets theorem and Oseledets decomposition, it started way before. So it started with the multiplicative ergodic theorem, and what is called Kesten and Furstenberg theorem, which they do it, I think, in dimension 2. I'm not 100% sure about that, but certainly in dimension 2. So maybe they do it at the very same time in higher dimensions. But in any event, this proof of Zimmer amenable reduction and this sort of approach to Oseledets theorem, if you want to see it this way, it would follow more these original steps than the standard proofs that are nowadays of Oseledets theorem. So it is much better in several respects. It hides some stuff, some important stuff that you can see it from Oseledets theorem. That's why sometimes Oseledets theorem is really still much better. But on the other hand, it's stronger, depending on what you are looking for. So, but let's see the context where it works. So let me do some definitions. An action of a group G on a space X and G a group H another group phi from G times X into H is called a cocycle if you satisfy the cocycle equation, which is the chain rule, essentially. So, oops, G1 times G2 over the X, this should be phi of G1X times phi of G2 applies to G1X. Okay, so since nothing is commutative here, the order is very important. Sometimes you can define left cocycle, right cocycle, which depends on whether also you are right action or left action, which has to do on how you multiply and how the action. And I'm using the notation here, Gx is alpha G of X. So this is typically standard so that you can forget about the alpha. And okay, that's a cocycle, and we call it measurable if it is measurable. Okay, and yeah, I think so. Yes, because I wrote G2. Actually, wait a second. You make no. No, yeah, I agree, but I also want to agree with my brain. So whether I want this to be a G1, G2 or a G2, G1.
Zimmer does it for right action, so.
Yeah, but
then maybe you want to write as X times G.
I want to write it this way.
So that was the left action.
Because in order for me to follow all the conventions, I just need to make it this the chain rule. And this is G2 composed G1.
Yes.
And that's why I wanted G2, okay. G1. So. Yeah, if not, it will have to be a right action, and then still we'll be happy, and there is not a problem.
I mean, of course, if your model is the Rodriguez derivative, then the other way around is
what to do? Yeah. Anyway, so we have this phi guy here, which is a cocycle when you satisfy this, and as always, or maybe not as always, but if you have some relevant measure as a background on X, and a relevant measure as a background for G, you can ask that all this is happening only almost everywhere with respect to the product measure and things like that. Okay? Of course, what would be a relevant measure for G? Hard measure. G, as always, is locally compact, Hausdorff, blah, blah, blah. So there is a hard measure. But even if you don't have it, you can still play with cocycle as you wish. But that's the standard. theory. And then, so here we assume all the time that these guys are measurable. And Zimmer theory is for the measurable category, so we really assume measurability. So you could assume infinity, reality, you assume whatever you want, the outcome will be just measurable. So it's no gain. And in most of the time, we will assume that we have an invariant measure for this action, even ergodic for that matter. But we don't need it here. So for the results, we will need to state it. Okay, so then what are for two cocycles to be cohomologous? So we say there is even one more general type of notion, but I don't want to go so general because one can split in different notions. Okay, phi I equals to 1 and 2. We say phi 1 is cohomologous to phi 2 if there exists C, a transfer map that conjugate one to the other is some change of basis type of map. Okay, so it means that if I do C of x, I do this, and I see it as through the eyes of this C, I get, if I put phi 1 here, and again, you want this for every g and x, but if you are just in an almost everywhere situation, and almost everywhere will be good enough for that matter. So that is that the two cocycles are cohomologous. And that's it so far. So now we want to enter into this amenable reduction. So what's the goal in Zimmer? So assume G is amenable. And actually, Zimmer then goes further and allows you to be more general than just an amenable group. Then you have to put a lot of hypotheses. And it's very useful in what he's doing. But in a sense, you really need the group G to be amenable, or at least the action of G on the space X to be good enough to allow you to do a lot of construction that one will need to be done. So you need a lot of averaging to be happening here. And you need that whenever you average, you have some limiting guy, and that's exactly what is amenability. So assume G is amenable, and assume also mu is a G invariant ergodic probability measure. Okay, so this will be the standard assumption, and we are looking to say something about a cocycle which takes values in SLNR. You could do other semi-simple Lie groups, but since any semi-simple Lie group modulo playing almost trivial things, you can embed in SLNR. We just do it for SLNR, and then whatever outcome you can restate for your semi-simple Lie group. Now I will state a not so enlightening theorem, but it's easy to state, which is similar amenable reduction. And then the point is to explain what really the theorem is saying. And actually, the proof is even more enlightening than what the theorem is saying. So Zimmer, amenable reduction, which, as I said, is heavily based on Furstenberg results, and it also has been rediscovered several times by different people. So it says the following, is that there exists H is not a good name, L, still not a good name, but an amenable subgroup and phi 2 or psi from cocycle. So this is a cocycle here, and Z from X into A SLNR. Here n is at least 1. So, of course, for n equals to 1 is trivial, such that Z gx inverse phi of gx c of x is equals to psi of gx. So you can conjugate your guy to be amenable. Okay, and I said amenable closed subgroup actually. Just to make sure. Okay, as I said, it may not be too enlightening, especially if we don't know really what are the amenable subgroups of SLNR. It's almost useless. So part of what I'm going to do now is give the description of the amenable subgroups. I hope it's all amenable subgroups. In any event, I will give the description of the amenable subgroup that will appear in this theorem. I think these are all amenable subgroups of SLNR because it's quite restricted. They are classified. So in SLNR, not in general. In general, it's a really huge problem. So if it were not a subgroup of SLNR and it were just amenable, it really will not say too much. But since it is a subgroup of SLNR, you have a lot. So let's go to examples of everything here. So as I said, n equals to 1 implies SL1R is the reals, and this is amenable. So nothing is said. So the theorem is empty in this situation. So, oh, because it's SL, it's not GL. Actually, but this is important. I think I want to do it, or I don't want. No, I don't need to do it. No, but I could put GL, but it's so. But this is useful actually for future use. So I will discuss it a little bit more later. But I could work in these guys, which may look a little bit broader than SL, but you can essentially write this as SLNR times R, which is not completely true because you have a plus minus also happening. But still, this is good. So, and then you can decompose by dividing by the absolute value of the determinant and multiplying by a plus minus absolute value of the determinant. You can decompose this into an SLNR cocycle and something taking values, a cocycle taking values in this group, which is amenable. and so you forget about this part. Okay, so that's why you actually concentrate on this guy and not on GLN. Okay, next, let's do now n equals to 2. So here are two main examples of amenable subgroups, and it's really the two paradigms of amenable subgroups in the world, other than the monsters and the strange guys. So is L SO2R, which is compact, and any compact group is amenable. B, we have the upper triangular guys, and this is also, so this is solvable and enclosed, so this is also amenable because it's an abelian extension of an abelian, and we know extensions keep amenability. The extension by amenable keeps amenability, and abelian groups are amenable, so this is not a problem. But there is the following group, which is also very important, which is the big problem here, in a sense, why the statement of the Zimmer theorem is not really so beautiful, because you have to suffer this last case, and then you are not allowed to state it so nicely, which is okay, is these matrices lambda, lambda inverse, and also I'm adding this matrix. So the group generated by these two matrices, which is just this group, and when I multiply by this, I'm just reversing and putting the lambda, lambda inverse here. So that's all I'm doing. But that's what it is. And this group is amenable because it's a two-point extension of an abelian group. So it's a C2 extension, or C4 because it has order 4, but anyway. So it's an order 4 extension, it's a finite extension of an abelian, and so it's as solvable as the previous one, even though it doesn't look like the previous one, it's still solvable, and hence it is, did I say solvable? It's still amenable, and hence it's amenable, and it's closed. And that's pretty much all it is. I think that all closed amenable groups on SL2R are subgroups of these three guys up to some conjugacy. And let me be more important than just this is a characterization of these three guys. Okay, so A corresponds to matrices let me just make sure I'm doing things correctly. Yes. So this matrix is in SL2R such that matrix is A such that the corresponding action on RP1 preserve a fully supported, actually not a given fully supported, in this case it's just lebesgue measure. Okay, in general we would have a group that we could call given mu a fully supported measure okay, I don't need it to be fully supported in principle. That's a measure on RP1 we have L mu equals all the A in SL to R such that A star mu is equal to mu. Probability measure. Okay, and then this case is the case of lebesgue. So let me write it here. So let me restate here. So such that A star mu equals to mu. Well, here we are considering, and we have that A lambda is SO. Okay, now you can conjugate SO to R by another matrix, and this will induce that you conjugate this lebesgue measure by this matrix. So instead of being the fully round measure here, it will have heavier support here, less support here, or the Radon-Nikodym derivative will be less than 1 here, larger than 1 here, but will be preserved by these other matrices which are conjugate to rotation. So this is A. Now the good news is that B has same characterization. For B, you take delta at the vector 1, 0. And then the mu is P. And then the even better news is C is also the same, is delta 1, 0 plus delta 0, 1 over 2. And this is this L mu in the setting C, where you preserve these two axes, because these are exactly the guys that, instead of doing the RP1 picture, we do the RP picture. So these matrices take this direction and either send it here or keep it here. So then you're preserving this combination of these two matrices.
For case number 8, mu has to be absolutely continuous. Is that?
This is, well, okay, that's a very good lemma. And that has to do with the, even though we don't fully need it, we will need a version of it eventually, but it's true. So if L mu is not the trivial group, then either 1 mu is equivalent to lebesgue measure in a very explicit way. Actually, I should put A here. Moreover, there exists Z in SL to R such that C star mu is lambda, so is that equivalent to lebesgue, so via this Radon-Nikodym derivative of pushing by C, and in this case L mu is essentially, I guess the C should be here, maybe should be the other way, doesn't really matter. Then your group is conjugated to this rotation, or B, there will be more cases than this ABC. Lambda is, not lambda, mu is delta at some direction B, in which case, again, there exists a matrix C such that L mu is C P C inverse, and the matrix C is bringing the vector V actually any matrix sending the vector B to the 1, 0, or to the line generated by 1, 0 will do the job. Then we have the case C. We are analyzing all L mu. The next case is a little bit more complicated, although I don't think it should be too much complicated. This mu is 1/2 delta V1 plus 1/2 delta V2, where V1 as direction is different from V2, and then similar L mu is pretty much the previous guy that we were discussing. Now, I want you to notice, maybe I should write this guy explicitly. Such that lambda is different from 0, and we have also this matrix. So I want you to notice that this guy here is rotation by 90 degrees, but since we are looking at RP1, this just intertwined this guy, but it's in a rotation manner. Okay, now we still will have one last case, which are, in a sense, the bad cases, because it's a lot of finiteness, which end up being subgroups of A, but the measure mu could come from a different source, which are the rotations, the rational rotations. Okay, so mu is sum of deltas at I over Q, or equivalent to this, so up to a matrix, and then you have all these matrices e to the pii j over Q. So if I want to do it, the RP1, I have to be a little bit careful. That's why RP1 really JQ, put a J here, and I should put some plus minus somewhere, I guess here, just to make sure I'm looking at RP1 guys. And
you also want average. So
yeah, you want the 1 over Q here, because you want probabilities, and then the L mu are these matrices, J's in Z. And then you can conjugate this by a matrix, as always. And I'm thinking of these complex numbers as being matrices, which is the corresponding cosine, cosine, sine minus sine. And this certainly is a subgroup of SO2R. And as I said, you can conjugate these guys, and that's it. So unless you're one of these guys, the L mu is trivial. So in particular here, and I'm writing really only this case because the conjugating this guy is quite much more complicated to write down. It's not that I'm taking Q points on the circle and the combination of these Q points of the circle. It's Q points which have a very specific configuration where you are rotating this Q point in a very determined way. So when you conjugate these guys to the standard rotations, they have to be equidistributed with respect to lebesgue. So actually, these Q points we are taking will have to be in a way that the measure of each of these intervals determined by this Q point have to be the same with respect to some invariant measure, which will be invariant by all the matrices here, and is equivalent to lebesgue. So I don't want really to go into all these details, but that's why this is the sort of painful garbage type of guys. So the generic guys are A, B, and C, and that's are the guys we really care.
So then that means that if I look at the group that contains a diagonal guy and a guy that is rotation by, let's say, 60 degrees,
then this group is
then it's actually everything.
exactly the closed subgroup generated by these two guys. Actually, well, no. So here we are looking at groups that preserve a measure,
Yes.
whose action on RP1 preserves a measure. Okay, so it's this type of groups. Then what we just said, what you just said was that there is no measure which is preserved by these two guys.
Yes.
Okay, because the measure is, or this group is not anyone on the list, which means that you should be in the assumption, which is L mu is different.
And so if I were to look at higher rank, then I would have diagonals, but I could also have any other matrix that would permute the axes.
That's in SLNR you will have many more things. That's why it's so much harder to state everything. So already in SL2 you have this, then in SLNR you have subspaces, and you have some configuration of subspaces that will be invariant. So you have finitely many lines, finitely many two-dimensional spaces, finitely many three-dimensional spaces, and so on, which they will be all permuted. And that's how it. So this is a second description. So this is a description through measures. There is a second description through stabilizing planes plus stabilizing some structure. So notice that both B and C come from stabilizing lines or configuration of lines. Even the item D comes from configuration of lines. But the item A doesn't come from stabilizing any line. It comes from stabilizing a Riemannian metric. Okay? So in this item A, you are, so even though we are writing this in terms of preserving a measure, what is actually more importantly happening is that there is a Riemannian metric on R2 which is preserved by rotations, or by these elements of the group A. So now, in light of this second or third example, I want you to state a Zimmer amenable reduction theorem which is false, but is really what you want to see of it. So you want to think that that's what it's telling you. And then there is false, so it's not accurate. So there are some things that you need to adjust. But philosophically, it is true. So what I'm going to do is I'm putting these sets, these groups of the form A and groups of the form B, so the compact groups and the upper triangular groups together. And I'm stating a statement about these guys, and I'm just pretending this C-type does not exist. Okay, so wrong statement, though philosophically true. Okay, too many pH. Is that there exists Z measurable such that CGX inverse phi of GX CX is some psi of GX and psi of GX is psi 1 of GX psi n of GX all zeros down there, and then of course you have here psi 1 2 of GX psi 1 n of GX, and the typical term is here in the middle psi ij of GX, so this is psi ij of GX n times n, and in such a way that the psi I, which is the psi I, this belongs to SO n, or okay, let's not put the S, so R times O plus times O of Ni R. Yeah, maybe let me do with more space here. So as I said, psi is psi I j, and the psi I belongs to R plus times O of Ni R. So these are orthogonal matrices multiplied by a number, so these are the conformal matrices. Psi ij of Gx is 0 if I'm below. So what is being below is I smaller than j, I guess. So it's fila 1, columna J. No, phi is larger than j. And that's pretty much it. So all the others can do whatever they want. So it's a block upper triangular matrices whose block in the diagonal are conformal. So real numbers times orthogonal. Okay, and as I said, this is not a correct statement because you may have this swapping of bundles. So actually what one can show is that there is an extension of the action, an extension of the cocycle, which is homologous to something like that. Or something which is a little bit hard to do in general, there is a quotient and a finite index subgroup so that you take values in a group like that. Okay, so the bad example is the group are the integers, the space is 0, 1 to the z, the measure mu is 1/2 delta 0 plus 1/2 delta 1. And then the cocycle here is have a generating matrix, so is A of omega x, okay, sorry, A of n omega is, well, this is in case n is positive. Case n negative, you just use the cocycle formula. So this is A of omega n minus 1 dot 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 A of omega naught, where A of 0 is the 1/2 2 matrix, A of 1 is this matrix. Okay, so for this cocycle, with respect to this measure, with all the statements that are here, you cannot make this guy homologous to a guy that I just described, which is an upper triangular guy. Okay? And it's because this guy has values in this C type of group, which you are permuting the horizontal and the vertical. Now, you could do some extension of the reaction and do some Z semi-direct product C2, which actually will take into account these guys, and then you can make the choices. You can do this stuff. There are other ways you can state this. Or you can just claim you take values in this group C. But then it's less nice than having this upper triangle. But what is important is this take values in conformance. Because this is what tells you that you will have an Oseledets theorem. So once you have this wrong statement, but philosophically true, how you derive Oseledets theorem from there is simply by you. So what does Oseledets give you? Oseledets give you a family of bundles, so that the direct sum is Rn. Actually, Oseledets give you a little bit less than that. That's the second Oseledets theorem. The first is only give you the flag, and it tells you that the top element of the flag grows like the norm, the next element grows like some other guy, and so on. So some multiplicative ergodic theorem happening. Now, here, what you do is you have to say what is the flag, and this is the flag. This space, this space, this space, this space, and this space. Okay? So the flag is this invariant space of dimension n1. The next element is the invariant space of dimension n2 plus n1, then n1 plus n2 plus n3, and so on. That's the flag. Now, here, no one is telling you that this is going faster than this. Okay, so the norm may not correspond to this guy. You have to prove something so that if this guy is faster than this, then this guy essentially can be killed, and so it doesn't matter. You can switch this guy above, and then you keep on doing this type of statements. And the point is that how do I compute the norm of this guy? Well, this guy, when I compute the norm, is a purely multiplicative cocycle. Okay, so it's not a matrix cocycle when I take the norms, because I have R times O. So the norm of the O part is 1. What you are only getting is these real numbers. Then you're just multiplying real numbers, which is a billion. It's a purely abelian cocycle. So you can apply Oseledets theorem to this guy if everything were L1. And that's part of the problem. If you really want to derive Oseledets from this theorem, you start facing problems coming exactly from this issue. So the norm of C of x may not be L1. Even if this is L1, this may fail to be L1. Well, the guy has SLN are valued, so if this is L1, this will be L1. So anyway, but this may fail to be L1, which means that the new, even if your original cocycle is L1 or log L1, this may fail to be L1 or log L1. But you will know a lot of stuff, and then you have to play. So I'm not going to do this argument. It's a fun exercise to see how to deduce Oseledets theorem from here using Birkhoff ergodic theorem. But what I want to emphasize is that you don't need the cocycle to be L1 or log L1, so log of the norm of the cocycle to be L1 in order to use this Zimmer variable reduction. So you have the bundles without the L1 property. That's certainly not possible through Oseledets theorem. So the L1 condition in Oseledets theorem is crucial to do anything. But here you don't need it. So the bundles are there. The way vectors grows on these bundles, that of course will depend on Birkhoff averages, and this again L1 will pop up. But the splitting or the flag is still there. Okay.
So the Oseledets theorem, in the Oseledets theorem, when you write, for instance, psi I, gx is in this conformal,
Yes.
the R plus part is constant for Oseledets.
No, for Oseledets it's not. Not. If you think of Oseledets, so in the limit you get the constant, but it's only in the limit. And it's true that once you have the writing, and this guy, if this guy were one-dimensional, so if you have Oseledets splitting where all the bundles being one-dimensional, then certainly you will have O1 here or nothing actually, and you get R plus, and you can apply Birkhoff ergodic theorem there. But Oseledets will not give you that. And in this sense also, yeah, that's a good remark. Zimmer, in this respect, is a little bit better in the sense that, let's say you are in 2 dimensions, and you go to Oseledets, and Oseledets give you both exponents 0. Okay, it's an SL2R valued, or you preserve area, you get both exponents 0. And then you don't get more, so it's quite a bit of information, both exponents are 0, but you don't get better than that. While Zimmer tells you, okay, you can make a change of basis, and your guy will look either this way, where the average of this log of A is 0, or the guy will look like cosine A of x minus sine A of x, sine A of x, cosine A of x, which has norm 1. Okay, so the norm of this matrix is bounded completely. So you don't need to care about anything. So the norm of this matrix oscillates as much as A of x is oscillating, but it's again a multiplicative way. So it's an abelian way of oscillating. So it's like Birkhoff is going to tell you how it oscillates. This norm does not oscillate at all. It's uniformly bounded. Of course, to do that, you have to pay by conjugating through a matrix C, and then, yes, you will have a norm of C of x times the norm of C of T of x inverse happening. So, and then this guy could be oscillating. So yeah, you cannot win on all directions.
So if Oseledets gives you 0 exponents, in fact, Zimmer tells you
how is this 0 exponent happening? Exactly. So these are happening either through rotations or through this possible twisting. B could be 0, so there may be no twisting at all.
The difference between the two is that the rotation has 0 exponent at finite time, the other one has 0 exponent as infinite.
Essentially, yes, exactly. Okay. Now, that said, I don't think I really have seen. Well, I have seen in random dynamics, but not for more typical dynamics, so standard z actions or action of the integer, iterator of a function. I haven't seen any use of this yet. I think at some point someone will use it and will have a very good theorem, but it's yet to be seen. So no one was able to do anything about these zero exponents, and knowing this epsilon more than saying, okay, it's not just zero exponent, they come in this form. So for your invariant measure, for almost every point, you have this look. What can you do about that? I don't know, no one ever have said anything about it. So there have been some uses in several sort of situations, but not really as much as one would wish from what it states. Anyway, so what I'm going to do next Monday then is to prove this Zimmer cocycle, this Zimmer amenable reduction, and the way of proving it is by finding this invariant subspace. So in this sense, it's similar to Oseledets, so you really need to find this subspace, and we're gonna find them.
By the way, before we finish, could you show the other board?
Yeah.
Psi 1 all the way up to psi n, but you don't mean that these are
the block.
1 by 1.
No, these are ni by ni. Yes. So each of these is an ni by ni matrices. But it's not any ni by ni, is orthogonal times r. Yes. So even though this is not a number, there is a number attached to it, which is the norm or the determinant, which fully describes the magnitude of this matrix.
So that n there should be some other number.
Yeah, this n, you are completely right. This should be n because I was saying SLN. So yeah, the sum of ni's is little n. Thanks.